Hi everyone. My name is Tianji. I'm a PhD student from the University of Michigan. Today I'm gonna present my summer intern work at Sigma Computing. In this project, we focus on Sigma's data discovery problem over data in cloud data warehouses. A little bit background of data discovery, which is a popular topic of data integration in recent years. Researchers have studied data discovery in different scenarios, including web table corpora, data lakes, and open data portals. The basic goal is to find connections between data sets and provide search functionalities beyond keyword search, especially for semi-structured data in data lakes. Our observation is that data discovery is not only a challenge for data lakes or web table corpora, but also a challenge for structured data in enterprise cloud data warehouses. When we talk with business users, they always face similar challenges of finding related data. We attribute this to a few factors. First, in large cloud data warehouses, few people have a good understanding of data and their relationships. Second, as cloud computing becomes easily accessible, data is added in a much less modal state. Third, business users, they may not have the expertise or the right tools to navigate their massive amount of data. Another more fundamental factor we consider is that the relational data model is great. It allows you to define important relationships like primary keys and foreign keys under a single schema. But there are relationships across schemas that are valuable to users but are not defined in a relational data model. Before we dive into the problem, let me also introduce Sigma because the problem we study is closely around Sigma's product. In a nutshell, Sigma is a web-based SaaS platform for cloud data analytics. As shown in the screenshot, it features Sigma workbooks, which connects to users' cloud data warehouses, Snowflake in this case, and provides spreadsheet-like interface for business users to perform interactive and collaborative analysis. So why does data discovery matter for Sigma anyhow? One scenario we found that it's LOOKUP. LOOKUP is one of the many functionalities from Excel that are familiar to business users. Sigma has the same functionality. Basically, a user write a spreadsheet formula or use the UI to add a column from another place. Under the hood, this is a cardinality preserving left join. A major hurdle of lookup is that users have to specify the source in spreadsheet formulas, which require users to have prior knowledge about what pieces of data are related. However, users may not always have such knowledge, and they have to rely on their data teams or more experienced seniors for help. This can significantly delay their analysis workflow, so it's not very ideal. Another similar scenario we found is join. Sigma workbooks also allow users to do data exploration starting from joining two tables. Users often have a table of interest at hand, but they do not necessarily know that many join opportunities in their data source. So we are well motivated to help business users to collect related data within and across schemas. We also want to understand some aspects of data discovery, particularly in our setting, that are less explored in prior work. For example, existing solutions, they assume at least a full path of underlying data, which is not feasible in our setting because it's both computationally and monetarily expensive to pull all the data out of the warehouses. So a question here is how to estimate joinability without access to full data. And from the company perspective, we also want to evaluate how much value data discovery can actually add to the workflow of business users. Let me give a slightly formal problem definition. Basically, given a corpus of tables and a user-selected column from a query table and a constant k, we want to find k candidate columns from the source in descending order of a joinability measure we define. The intuition we had to solve this problem is to use embedding representations from deep learning models. The hypothesis is that embeddings can encapsulate column semantics and serve as a proxy for the joinability. Here, we simply consider the cosine similarity between embeddings as a semantic column joinability. The figure gives an overview of our prototype. It consists of two pipelines, which we'll introduce in turn in a moment. But let's first talk about the common part in both pipelines, which is column embeddings. At a high level, the embedding representations depend on the embedding model. We consider three factors when we determine determine what model we want to use. First, whether the model is trained over tabular data. Many works have shown like models architecture towards tabular data manifest better performance in downstream tasks. The second factor we consider is the size of the training corpus. Empirically, the larger the training corpus, the better the generalizability of embedding representations. We also consider the efficiency of model inference. We could have taken a very complicated model, but it also carry like heavy inference cost. Ideally, we want to have a middle ground of the quality of embedding representations and the efficiency of model inference. Usually, prior work they take whatever state of art in the literature. Here, a challenge is that how to adapt embeddings for our own enterprise data and for our joint discovery. So in our latest iteration, we are experimenting with a new technique called contrastive learning. The basic idea is to provide joinable pairs of columns and non-joinable pairs of columns to the model, so we can fine-tune the embeddings such that they are more adapted for our data. Now we have embeddings, we still need to address the search problem. To avoid exhaustive linear search, we employ locality sensitive hashing. The basic idea of LSH is to maximize the hash collisions for similar inputs. In our case, we want to approximate the cosine similarity between embeddings, so we rely on random projection, which essentially insert many hyperplanes in the vector space as hash functions. Once we build up the index, we are ready to serve queries. A user can simply select a column of interest, and then the query column is embedding using the same model and hashed in the LSH index. And the index will only search within the sub-universe of embedding vectors that shares the same hash as a query vector. We also contribute an interface that manifests our prototype in Sigma workbooks. From left to right, a user can simply select a column and right-click on the discovery option. And then our prototype will provide a ranked list of recommendations. A user can get better hints, browse the recommended sources, and add whatever column of their interest to the current table. Let me also briefly describe our experiments. So we considered three repositories. The first repository has data sets classified by their file sizes. So there are 4 subsets, which translates to the average number of rows in the data set. And each table in this data set has independent schema, so we use it for evaluating across schema domains. And we also study the effects of different data sets to the query response time. The second data set we use is for primary key, foreign key detection. And the third repository is a complete data for demo purposes, we applied our prototype on this internal data and did some ad hoc discoveries, and we found some interesting joins. Since the first two repositories have ground truths, we also compare our prototype with two baselines that report on like enterprise use cases of data discovery. As shown in the slide, figure A and figure B shows that for across schema joins, our prototype, the green line at the top, consistently obtains higher precision and recall compared with two baselines. And for primary key, foreign key detection, our prototype compares favorably with an ensemble approach. For efficiency, what we found is that if you scan the entire data and build whatever profiles, like in our case, embeddings, it is actually very expensive and won't give you interactive speed. And also, index lookup time is only a portion of end-to-end query response time. So for our deployment, we actually need to optimize other factors in the pipeline, like data loading and embedding inference. So back then, we just take a simple approach of sampling that significantly reduce the index lookup time and end-to-end query response time. And a little bit surprisingly, we need as few as 10 samples to get effective embeddings, and that doesn't affect the performance very much. This is still an ongoing project. We are working on deploying this prototype in Sigma's staging environment, so we can conduct a more formal user study and also evaluate our prototype with internal data. The figure on the right shows like how we fit our prototype into our backend architecture. Basically, our prototype will be a backend service that gets hooked to a middleware that handles all the communication between the front-end web app and all the backend services in Sigma. A few problems we are currently need to address is for deployment in containers over Kubernetes, we need to envision CPU and memory usage. And also when the service is done, like we need to quickly rebuild the index so the customers can have the query service back. As a conclusion, we present WarpGate, a prototype for semantic join discovery in an enterprise product. And we show that our embedding approach is both effective and sample efficient. And we also expect to share more experience and lessons of deploying the prototype and evaluate value to the end users. And thanks. I can take questions from you.